Hello, today we will calculate the mass of a black hole by only looking at observational data of a star that orbits that black hole. Here on the left side I will take you through the steps, and on the right side you see the accompanying Python code. Given us the mass of the star here, and in the Python code you find that here. Position of a black hole is only visually represented here, and the star's motion around the black hole in one full orbit in 2 dimensions, x and y coordinates, is given in this data file here. Time steps between the observations is 1 day, given in seconds right here and labeled delta t. Now, how do we find the mass of the black hole? We'll use the gravity formula and rewrite it, solving for m1. This will our black hole mass. We already have gravitational constant, and m2, this is the mass of our star. Now to find these two other factors, Fnet and the distance between the star and the black hole, we will, to find the Fnet force, we will subtract the position number 1 of the star from position number 2 and divide it over delta t. That gives us a velocity. And if we then subtract position number 2 from position number 3 divided by delta t, we get a second velocity. So we have an initial and a final velocity. The Python program does that right here, while it differentiates between x component and y component of a velocity. If we then multiply the velocities with the mass of the star, we get momentum. And in the Python code, we did this right here. Subtracting the final momentum from the initial momentum and dividing by delta t again, we get a change in momentum over change in time, and this is the net force acting on our star. And in the Python code you can see that here, delta p, and here is Fnet is this dp dt, delta p divided by delta t. Now, to find the distance between the star and the black hole, we simply calculate the magnitude of the position vector of the star, since the black hole is already assumed to be at the origin of our coordinate system. So here's the calculation for that. And finally, here's the calculation of the black hole mass. This is this formula right here. And so let's run this code. And I told the program to print the black hole mass at the end once it's running the simulation. Okay, so here is the mass of the black hole in the end. So roughly 10 times the mass of the star. Now, also in the visual presentation we saw the parallel net force component vector and the perpendicular one. How do we came about with those? For the parallel component of the net force, we simply take the unit vector of the momentum and multiply it by the change in magnitude over change in time. So this is the parallel component. I call it the acceleration deceleration. And the perpendicular component we simply get by subtracting that parallel component from the total net force. So we arrive at the perpendicular component. This is the turning radius. The Python code does that right here to calculate the parallel component, and here to calculate the perpendicular component. Let's be careful, because Fnet is not equivalent to the change momentum over change in time, because our Fnet is the cause and what we calculate is only an effect. So, but we assumed it the other way around to get an approximation on the net force of the mass. We assumed that this was equal in our calculation, but in reality it's not. It's only an approximation. Now another question was, what if we replace the black hole with another black hole, but yet the motion of the star orbiting it remains the same, and the only force acting on the star was the gravity from the black hole? Could we find a different mass of the black hole? No. The answer has to be no, because we would see a change in the motion of the star orbiting the black hole. So we have to assume, if the motion doesn't change, we have to assume that the mass and the position are the same. Thank you.